So, today we will focus on one of several possible interpretations of the definition of differential privacy, which is hypothesis testing, and I would explain gradually what it means. This perspective will be important for two reasons. One is, I think this is one of the more natural ways to justify this definition, and in some way make all of the choices of all of the quantifiers and the terms that are in the privacy definition sort of self-explanatory from first principles. And the second is that this is the first step in some ongoing process we will go through in this course, where we will see how in some sense privacy in the way we learn from data and the notion of generalization are tied to each other. Okay, so just to recap, what did we do in the last 2 weeks? We realized that people proposed various anonymization techniques throughout the years, and each one of them eventually we found some problem in it. Then reconstruction attacks came and showed that there is a systematic way that any privacy notion will break if you don't have some properties. So it's not just a matter of, oh, we haven't found the right definition, it's more general. Which means if we want to be able to somehow really guarantee privacy, we need some formal, rigorous definition. And then, as you already know, differential privacy was proposed. But I don't want to accept it as a given axiom. Instead, in this lecture, we will try to derive from first principles some privacy notion and see where do we land. So we will sort of shift to the adversary's perspective throughout this lecture, meaning we will be the bad guys, we will put on the red hat, and we will try to understand how can we provide the best opportunity for the adversary, and then see its limitations, which are basically privacy. Okay, so let's think, what is the strongest adversary that we can consider? So it needs to be an adversary that doesn't know at least one bit of information, otherwise there's nothing left to protect. But other than that, they know everything that you can know. So what does it mean to know everything that you can know? It means having full knowledge of the entire data set except for the one element we're trying to protect. It means knowing the identity of the element we're trying to protect, or the two elements we're trying to distinguish. Right? We think of it as a story of, well, it's either me or you that participated, or it's either me with one feature or me with another feature, or it's I either participated or did not participate, but there's like some bit of information that is missing. But other than that, the adversary knows everything. And furthermore, the adversary also knows the inner working of my private or anonymizing mechanism. So if I have some algorithm that truncates the data, that adds noise, that uniformly samples elements, that, I don't know, whatever, we cannot hide it either. The adversary knows that. Okay? So my claim is that this adversary that I just defined is the worst case adversary. We cannot imagine an adversary that is stronger than the one I just described without just saying, well, the adversary already knows the secret bit of information, so there's nothing left to protect. Make sense? Okay. So, at this point, you can disagree with this very pessimistic perspective. Maybe I can hide the inner workings of my algorithm so that the adversary wouldn't be able to figure out how exactly I sample things. Maybe the adversary has only distributional knowledge over the rest of the elements, but not the exact identity of the other elements. Maybe I can have all sorts of weaker, looser assumptions, and accepting them or not is not so much a matter of a mathematical definition, but more a matter of taste to some extent, right? You would say, oh, but how would the adversary know all of the other elements? And then I can tell you, well, it might not know all the other elements, but it might know a significant portion by, having some combination of other sources of information, etc., etc. And then, if you know a large enough portion, maybe it already suffices to figure out if a certain element is there. You might be able to hide your inner workings to some extent, but maybe not enough of the important stuff. Maybe it doesn't know. It can figure out that you add Gaussian noise and it doesn't know exactly the variance, but it can estimate it. I don't know. So basically, for all quantifiers that we're used to in the differential privacy notion, come in a way from saying we don't want to make assumptions on the adversary, because if we make assumptions on the adversary, they might break. And this is indeed the part where if someone will tell me, I don't consider this a reasonable assumption, I would use a weaker assumption, I wouldn't be able to justify the strong assumption. I would be able, probably, to point out that they cannot justify the weaker assumption either. It's a matter of this. So this part of the story, I am not trying to derive from first principles. I'm reflecting the fact that we need to make a decision, and no decision that is weaker than the worst case can be easily justified. So, at least let's consider the worst case, because if we manage to protect against the worst case, then we definitely protected against everything. Okay, so this is the world we're at. The attacker knows everything but one piece of information, one bit in a way, and it needs to figure out what happened. Do you have a framework from the general mathematical computer science, theory of computer science literature that this sounds somehow related to? Sorry?
Cryptography, maybe?
Why is it a matter of cryptography?
Well, you're trying to hide something beyond everything else. And cryptography is based on the fact that you're revealing some information and hiding another. And can the attacker get to something? Can he pull something out?
Yes, but cryptography has the property where what you want is that the entity that observes the data and is not supposed to be able to decipher it should get nothing out of it. That is the optimal thing, right? Like what we aim for, we don't necessarily manage to get there, but what we aim for is that when we have Alice, Bob, and whoever it is that is eavesdropping, then both Alice and Bob have all the knowledge about the information, about the data, whatever it is, and Eve has no knowledge. Hopefully, we maybe can't get to no knowledge, but we can get to very small knowledge. Or
in really good cryptography, we can, in theory, even if Eve has lots of knowledge, we want to be able to do stuff. Right?
No, knowledge about the thing that we're hiding. Again, she might have information, auxiliary information, but the thing that we're hiding, if she already knows, there's no point in hiding. So there's whatever it is that we are hiding, there's some part that is the unknown bit, or several bits, and that part she doesn't know, otherwise there's nothing left to hide.
Technically, assume she knows some of this stuff.
Okay.
You don't know which of it she knows, you just want to hide whatever she doesn't
But
know.
there's something that we're hiding, and that's something she doesn't know. And what we hope is that from her perspective, the options will be practically the same, uniform, no knowledge. Okay. we can't do that because if we live in a world where my participation in a data set has zero effect on the outcome, then the data set did not use my information. Then the outcome did not rely on my information. But then, okay, now replace another one, and eventually I can replace the entire data set and still. So obviously that by definition means that we're having an algorithm that achieves perfect privacy via zero utility. There's a very easy algorithm to be perfectly private. Just output a random or a constant number.
Well, to be honest, in this case, there is a similarity to cryptography that you would say here. Over here, you want to say that the adversary has everything other than one bit. You didn't specify which bit the adversary doesn't know. For all we know, you want every individual bit to say, even if you know everything else, this bit is it.
Yeah.
Like, the first bit is it. Even if you know everything else, including the second bit is it. Even if you know everything else, the third bit is it.
That absolutely. With the inherent difference between cryptography and privacy, where in cryptography, completely destroying the utility of the eavesdropper is not a problem. It's in fact, it's even a desiderata.
Okay.
Where in here, we're trying to do something that on first glance seems nearly impossible. It needs to contain some information because otherwise it's garbage, but it needs to not contain enough. So, that already means that there must be probably some kind of randomness. Because if everything is deterministic, so there's exactly two options. Either the output did not change by flipping this element, in which case this element was completely ignored, or it was changed and then, well, the observer, the attacker, can perfectly distinguish between these two options because the attacker knows everything else. Okay, so it's clearly random. But what is this setting if we have two options about the random thing that is generating this output and you're trying to distinguish between them? So statisticians and computer scientists both consider this setting using two different languages that are exactly the same up to renaming. Either hypothesis testing or binary classification. Hypothesis testing, and the statisticians, they usually think of it in terms of there's some null hypothesis, the baseline that I have that I want to disprove. Say, I think the average salary of men and women is distributed about the same. And there is some alternative hypothesis. Let's say men typically earn more. And then we get a random sample out of a distribution. What is the distribution? Well, if men and women are the distribution of their salary is the same, so now that induces some distribution over the data set that I will sample that contains, well, about half and half men and women, and some salary distribution, and the salary distribution of men and of women is supposed to be about the same, but of course there's some probability that I will get a higher average salary for men or for women, even if it's the same. And then the alternative hypothesis that says there is a difference induces a different distribution. Okay, so this is one perspective. Another perspective is binary classification, where you say, there is, my learning task is to label something as 0, 1. And then I do it based on some signal I get, the features of the element or whatever. And then there's some randomness here in the features and maybe even in how the features map to a label, right? In some like non-realizable settings, a label might not be a deterministic function of the features. And again, what happens here is there's the distribution of whatever features for the elements that should be labeled 0 and the distribution for elements that should be labeled 1, and we're trying to guess. Okay? And in both cases, we look at it in the following way. So I would use the notations of H0 and H1, but it is and the reason I will do it is because we'll get to it in a moment. We typically use terminology like true positive, false positive, etc. So we have some asymmetry between what we call positive and negative, but this asymmetry is not something inherent. Like in statistics, there is real asymmetry because there's a null hypothesis and then there's an alternative, and they have a different role. All I'm expected to do is to disprove the null hypothesis. I didn't prove the alternative one. In binary classification, just replace 0 by 1. So it's meaningless. Here, in privacy, sometimes you have asymmetry. Let's say if it's me versus you, then, well, there's symmetry. Like it's either privacy for me or privacy for you. But if it's like me participating versus me not participating, then there's some asymmetry. So terminology-wise, I'll call it H0 and H1, null hypothesis or not, positive or negative, but it is important to remember, this is completely symmetric from the mathematical perspective. Okay, so what do we have? So we say there's two distributions, H0 and H1. Here there are two Gaussians, same variance and different mean, but it can be any two distributions. And I sample an element from one of them. And given that element, I am trying to guess whether it came from the first distribution or from the second distribution. This is the game. In hypothesis testing, it will be, well, based on this element, I might say, oh, I disproved the null hypothesis. In binary classification, I'll just give it a classification, and I might be right and I might be wrong. This is the setting. Make sense? Now, notice that in this case, it doesn't matter what is the dimension of the distributions. It doesn't matter how complex the mechanism generating them is. It doesn't matter what are the data sets if we're going back to our world. It becomes a very simple 2 by 2 matrix, which is typically called confusion matrix, which corresponds to the following thing. Did it come from distribution blue or did it come from distribution red? And did I guess blue or did I guess red? That's it. No more options. Right? So let's look at it. Notice I am simplifying here by assuming, currently with no justification, that I will guess based on the output by just defining a threshold, saying there is like some value, anything to the right of it I will guess blue, and anything to the left of it I will guess red. This is not necessarily the best decision rule. I might have some more complicated definition where like there's different sections, and here I guess red, and here. But regardless, I have to color the entire regime by either blue or red. Like the rules of the game here, I always guess. Okay, so basically, when you look at it, there is the regime I would guess blue, there's the regime I would guess red. There's the probability to land in each one of them based on blue and red. So this is how we populate the confusion matrix. So in this representation, the columns are what the truths, the reality, and the rows are the guesses. I could have flipped them, of course. And each one of them can be positive and negative. And again, positive and negative are like arbitrary names. 1 and 2, blue and red. All right? And therefore, we use the notations of there's true and false, positive and negative. And just to be clear, positive and negative means what did we guess, and true and false means were we correct and were we not. So you see, this row, both of them I guessed positive. In this case, I was right, true positive, and in this case, I was wrong because it's actually negative. Okay? So notice these are not probabilities, these are events. There are exactly 4 options. It came from this distribution, or for that one, I guess this or I guess that. That's it. Let's look at it visually. So, in the left plot, we're considering the world where things actually came from the red distribution. So, the part under the curve to the left of the threshold is the part that I would guess red, which in this case will be, let's associate red with negative. So what is this section, the section where, oh my, this is impressive. This section, what is it called out of the four options? This is, what did I say it? Oh, that's a good point. I spoiled everything.
Yeah.
Yes. So this is true negative, and this is true. This is false positive, and the other option is it's flip. And since the area under the curve is under the probability distribution curve is the probability, so we clearly see here visually, without knowing the exact numbers, that the probability of guessing red when you are sampled from the red distribution is larger than the probability of guessing red when you were sampled from the blue distribution. I don't know exactly by how much, but this is clearly not a stupid decision. It's like somewhat correlated with the truth.
To be honest, we care more about the probability of guessing red when you're in the red region versus the probability of guessing blue when we're in the red region. Isn't that like more important than the probability of guessing red when we're in the blue region for red?
So what you're saying here, and this is the important thing, is that so far I did not discuss the question of what is the optimal decision. Why did I not discuss it? Because there is no such decision that is optimal before we provide another parameter. So far what we have is a trade-off. So what does each decision rule induce? It induces a false positive rate and a true positive rate. Of course, they can also have the false negative rate, but we choose to. What does it mean? The false positive rate is the probability that I would guess true, that I would guess positive incorrectly, meaning that the true value is false. I am sampled from the true value is negative. I sample from the red distribution, and yet I guessed blue positive. And the true positive rate is the probability that I guessed positive and I was correct. So in other words, I'm comparing the two blues. The blue when it should have been blue, and the blue when it incorrectly blue. Okay? Of course, I could have compared the two reds. It's again symmetric. And any decision rule defines a point on this plane. So this is a ROC plane. I never remember what ROC stands for. Only thing I do remember is C does not stand for curve. So saying ROC curve is valid. It's not like, a Melech King George or all those weird things. ROC curve is the correct. Yeah. So, what is this plane? This basically tells me the following thing. For any decision rule, I can tell what is the probability mass of deciding positive under when the element, because now basically the decision is a random variable. There's something is drawn from the distribution. The distribution is arbitrary. It doesn't have to be numbers. It can be any kind of elements. But eventually all of these elements, given a decision rule, the decision rule maps all of them to exactly two values. There's the distributions that will lead to a guess positive, and there's the elements that will lead to the guess positive, and there's the elements that will lead to the guess negative. These are the only two options. Okay, so basically this is a binary distribution. The distribution of guesses is a distribution over two values. So, and the true positive rate and the false positive rate are basically the probability of landing on element 1, the element corresponding to positive, under the first distribution, under the second distribution. So now, any decision rule defines these two probabilities. So it defines a point on this plane corresponding to the probability of guessing positive under hypothesis 1, hypothesis null, and hypothesis 1. Okay, so there's a point. So if I look at this distribution, this decision rule, so there's some probability for this, some probability for that. So given the loop, give it a look, try to remember or use the notebook to see what the value is, and give me, a general vibe of like where, give or take, in this plane should the corresponding point be.
Given the images that we have?
Yeah.
The corresponding point, meaning
So the point has two coordinates. The x-coordinate is the false positive rate, which is basically this blue, the probability mass here. And the y-coordinate is the true positive rate, this blue.
0.6, 0.3 approximately.
0.6.
No, 0.6 on the true positive rate, 0.3 on the false positive rate, approximately.
All right, so let's start really short. This is clearly less than half. I don't know if it's 0.2 or 0.3 or 0.4, I don't know, but like something like that.
Oh wait, I'm looking at the negatives. So 0.7, 0.4.
Should be
Yeah.
whatever, right? But this is like 0.2, 0.3, 0.4, something like that. This is 6, 7, 8, something like that. Okay, so this should be somewhere. This is the 3, this is the 6, 7, I don't know, somewhere here, give or take. Maybe higher, lower, whatever. Clearly above the diagonal, right? That you can say for sure. Okay, let's think about this plane. So question 1, what is the desired point? If you were able to create the perfect decision rule, where would it land?
Top left.
Sorry?
Top left.
Top, why top? Because we want
Positive.
highest true positive.
Never get-
Why left? Because, right? So the best we can hope for is being in this corner. Next, what is something we can always achieve?
Any point on the
the
diagonal.
identity by just
What is the identity? I think you're both
Any point on the diagonal.
right. Okay, so let's say I want to achieve the point, 0.2. How can I do that?
Flip a 5-sided coin.
Ignore the data, flip a coin. It doesn't need to be 5-sided, it's going to be biased. A biased coin, 20% of the time I would guess positive. Well, then I'll have a false positive rate of 20% and a true positive rate. Okay, so the entire diagonal is achievable. And in a way, that means that anything in the top triangle is just like being an idiot. You can always, if you're guessing, right, if you have a predictor that is below random, you basically have a better than random predictor by just flipping it. So for all intents and purposes, the top half doesn't exist. Okay, now sometimes sorry, the bottom half doesn't exist. I said the top. No, sorry, the bottom half doesn't exist. Okay, now in some cases I might be able to achieve that corner. Let's say if the two distributions are deterministic ones. If H naught is always returning the value 3 and this one, the H1 the value 7. Well, that's great. But obviously I typically won't be able. So here is a question I can ask. Given that I fixed one of them, what is the best I can get for the other? And this goes back to your question, Itza. There is no one point that is the best here. There is a trade-off function that says for any amount of error rate you're willing to accept in one direction, what is the best success rate you can get in the other one? And this is where statistics and computer science differ. Computer scientists tend to look at it as a true positive rate as a function of false positive rate, and statisticians sort of effectively rotate it in 90 degree, and what they get is false positive rate as a function of false negative rate, or the other way around. But it's like, again, renaming. So I chose this because typically more people saw this curve in Introduction to Machine Learning, but it's important to remember that if you read the statistical literature, nothing is different. Okay? So for any point on the x-axis, there is the highest achievable point on the y-axis. I don't know what it looks like, but there's something like this. This is called the ROC curve. The ROC curve is the, in terminology of game theory or whatever, it's like the Pareto frontier. Right? It basically tells me for any value in the x-axis, what's the maximal or minimal, depending on the context, in the y-axis. And there is some curve. And so far, I don't need to prove anything to claim that the curve exists. Right? That's well, you might ask, but who knows? I can achieve every value. Like maybe I can achieve 0.2 and 0.4, and I can't achieve 0.25. But then I can always just ruin my. Like if I can achieve 0.2, I can always just ruin it a little bit. I can always fill it. ROC curve has a whole bunch of properties that I will not get into. It's convex, for example. Concave in this representation. In trade-off, it's convex. There's all sorts of properties. I won't get into them because they're not relevant to this lecture. But what is relevant is it's monotonically increasing. Right? That is, again, you need to prove it, but it's really trivial because like if you can achieve a certain level of positive rate with a certain negative rate, then obviously you can, if you're willing to have more mistakes in one direction, you can have less mistakes in the other direction. And it's always above the diagonal, because again, anything like the diagonal is achievable via random guesses, so obviously the optimal one can be below the diagonal. Right. So this is the language we think of when we discuss hypothesis testing or binary classification. So far, so good? Notice that the ROC curve itself is a function of the two distributions. The point on the ROC we land on, that is a function of the decision rule we made. When do we guess yes and when do we guess no? But the shape of the ROC curve has nothing to do with the decision rule, with its specific decision rule, because it's described by the optimal decision rule. So once I define the distributions, I'm done. So in this example, I have two Gaussians. They are 1 unit apart. So one of them is centered around, let's say, 0 and one around 1. Of course, they can be around 7 and 8. It doesn't matter, but like they're 1 unit apart. And they have different values of variance or standard deviation. Okay? So if the standard deviation is 0.2, so what does it mean? We have two distributions that are very concentrated around their mean. Their width is significantly smaller than the difference between the means. So nearly all points land, if we go back to this picture, these are far apart from each other, so you barely have points where it's hard to tell. So you might even not notice the blue line. The blue line is the one that looks almost, it almost reaches this this corner. You see here this tiny thing, it's this one.
You see the curve more than anything.
Yes. Okay, so basically, with sigma equal 0.2 and gap in means that is 1, you can achieve probably, I don't know, 0.98, 0.98 or something. Sorry, 0.02, 0.98. And as the variance grows, the difference, it's harder and harder to guess. Still, if you have variance 5, I mean, you're better than a random guess, but not by much. Which is not surprising, because the difference between the means is a fifth of the typical error, or typical distance from the mean. Okay, so in order to make sure that we fully understand what we did, let's have a concrete case study. So let's consider two binomials. Okay? One of them, both are over 5 elements. One of them has probability half, and one of them has probability of bias 0.24. And we want to compute the ratio of the probabilities for each one. Like how much more likely is each element under each probability, and you know what? No, let's not do it now. Sorry, this slide should have been later. Forget it. Okay. Now comes the fun part. So now I want to make sure we understand what is happening in this decision rule regime. So again, as I said, in this setting, we have two Gaussians, same variance, different mean, and I'm considering only decision rules that are a threshold on the line. So far, I'm not claiming this is the best decision rule, but it's a family of decision rules. So now let's see what happens when I change the threshold. All right? So let's take this value, for example. How should we interpret it? So first, let's look at the x-axis. It says that, let's have this number. It says that any outcome that is below 2, I guess 1, red, 0, null, and any outcome that is above 2, I guess blue. I can look here at the two distributions and approximate how much probability mass do we have for the event of guessing blue or red under distributions blue or red. And the right plot shows me the point, this yellow moving point, that tells me, well, what is the false positive rate and true positive rate that this decision rule corresponds to. So, as we can see, the probability here is relatively small, right? This seems like a small probability, and indeed, it looks here like, 0.0 something. And the probability here is not so negligible, so it seems like it's 0.17 or so. Okay? I put the guess here. I have a higher false positive rate, higher negative rate. A natural option would be to put it exactly in the middle between the two. Do you have an intuition of where exactly will this yellow point land in this case? Like what would be it's going to have some very natural property in this case.
It should be the best ratio, like between the true positive rate and the false positive rate.
Not ratio. You can think of it as sum. Right? If you care about, if you are completely symmetric in your treatment of positive and negative, and you want to minimize just the probability of an error, then this is the one. And where does it land? Where visually does it land in this ROC plane?
If you were to flatten the if you were to turn the diagonal 45 degrees so that it's flat, it would be at the top of the cone. Basically.
I'm low. I don't have the visual image.
Say, if you were to rotate this so that the diagonal would actually be flat, and then this function would be
Yes.
this, then that would be the top of the function.
Correct.
That would
Okay,
be
so
the-
let's separate. There's 2 points here. The first is that when we minimize, there is some challenge in teaching this kind of thing, because on one hand we want to start with very natural, easy, clean examples, and on the other hand these examples sort of hint toward assumptions that are not necessarily true. What do I mean by that? For example, this is symmetric along the other diagonal axis. If we want to minimize the sum of the errors, then what are we minimizing? We're minimizing basically this value, the value that is the gap between 1 and the y coordinate, because that is the false negative rate, plus this value. Right? So what we really care about is not exactly what you described, but this like L1 norm of this location. In the specific case of two distributions that are symmetric in some way, and I'm not getting now into the exact definition, but if they have the same variance and different means, and they're symmetric around their own axis, then it's very easy. Then this point must land on the diagonal y equals 1 minus 6, right? The other diagonal that we didn't draw. Okay. But again, it's a matter of taste. If it's some drug that you administer, or some medical test or something like that, then the danger of having an incorrect assumption in one direction and a different direction might be completely different. So therefore, none of the points here are in a way inherently better or worse than others. But as the previous slide showed, different pairs of distributions induce different trade-offs. So in a sense, if I have some medical test that with some probability will indicate that a patient has some condition when it doesn't, and with some probability will indicate that it doesn't have it when it has. And now I need to choose between several tests. So choosing between the several tests is choosing between the trade-offs. Given a test that I chose, now when do I tell the patient that they have the condition, or when do I decide to give a treatment or whatever? That's choosing a point along the curve that I defined once I chose the specific test.
Privacy. The adversary is choosing the point on the curve. We want the adversary to have bad choices in all cases.
Yes, but in a way, what I'm trying to do now is forget about the privacy background, not because I'm trying to hide something, but because I am trying to ask ourselves, what is the best way to think about the task of binary classification? What are the options? Where do we? What can we do? How do we find the best decision rule? And then we'll go back to defining privacy. Okay, so let's take a short break. Shai